Now that we've done the three types of bonding, the metallic, ionic, and covalent, we're going to look at the Van Arkel-Kettler triangle of bonding. And so the syllabus says you don't need to be able to do this one here. So the electronegativity difference divided by 3.2. But it does say that you need to be able to use electronegativity data and put things on here. So you need to do everything else. So just having a look at this and trying to make sense of it. So you can get from this equation that the largest electronegativity difference is going to be 3.2, so it'll be 100% ionic. And so that there is the most you can possibly get as far as ionic is concerned. And that would make sense because you're going to take the most the most reactive metal and the most reactive non-metal, the one that's going to give off the most and take the most. And that's what you're going to get at the top there. Now, if you're going to look down here, now this is average electronegativity. And so for the metals, they're not very electronegative, and so the electrons are free to just float around in a sea. And so they're delocalized. And so you're going to have the lowest electronegativity, average electronegativity for metals. So that's why that's at that end. And then for covalent, you need two really strong electronegative elements in order to lock the electrons in place in the middle. And so that's why you have, over in this corner over here, the most covalent substances, because they're going to be locked in place. Now, realistically, this is going to be the maximum for locked in place. This is going to be the maximum for electrons freely floating around the cations. And this is going to be the maximum for having electrons all go over to one side. So everything else is in between. So obviously it's, some things, they're going to be maybe some ability of the electrons to move between the two elements, or there's going to be some pulling for both from both corners of both nuclei. And there's obviously some element of it pulling to one side more than another. And so you basically grab the electronegativity difference and the average electronegativity and plot it and see where it lands. And that's what you're going to call it, either covalent, polar covalent, ionic, or metallic. And so these ones here are the most extreme we can get. So the bottom left-hand corner for losing the electron, and the top right-hand corner for gaining the electron. And so that's as ionic as you can get. The most covalent is the strongest, the one that can pull the two together the strongest. And so that's the top right-hand corner, ignoring noble gases. And then the bottom left-hand corner is the nuclei that have the weakest ability to hold on to their electrons. And so they're the classics, and they're the best that we can get into the corners. Okay, so moving on from there, you're also asked to look at period oxide trends across the periodic table. Now, if you use your data booklet one, you'll get some polar covalent across here. And so I just found the best one I could and plotted the rest. And so you can see that these ones here in the ionic part are becoming less and less ionic and more polar covalent. And so these ones here, this one here is now covalent, polar covalent, and these ones are also slightly polar covalent, and this one's just coming up to the covalent. So as you move across period 3, you're moving from ionic to polar covalent to just normal covalent. So there are also covalent networks to simple covalent molecules as well. And so when you have these simple covalent molecules over down here, you're going to have the low melting boiling points. These polar covalents are going to have higher melting boiling points, and then they become network solids even higher. And then ionic substances classically have the highest melting boiling points. So you just take the characteristics of ionic substances if it's in that area, or network solids, or polar covalent substances, or non-polar covalent substances as you go down. So find out where it is, and then try and also get a good idea of whether you can work out whether it's a metallic bond, covalent, ionic, polar covalent, just to double check and back up your ideas, because some of them are sort of in between two areas. Okay, so Some of these are using the 3.2 and some are not. So how do you tell which is more ionic, sodium chloride or lithium chloride? You're just going to have to do the calculations. So there's the difference in electronegativity, which you'll plot here on this side, and the average electronegativity, which we'll plot on this side. So if you've done the calculations for that, you'll find that sodium chloride, if you'll have to get a ruler or something, and you'll see that the distance to the corner of ionic is much shorter. Not much shorter, but just shorter. So sodium chloride is technically more ionic than lithium chloride. Now, some of these calculations have 3.2 in it. It means you don't have to calculate it, but maybe you're given it in a database question still. And so these ones you may well have to do. And so you grab diamond, silicon dioxide, zinc, copper, find the electronegativity values, and then plot this and this together, and you'll find silicon dioxide is in the polar covalent area. Carbon diamond as a covalent network lattice is down here, and copper zinc alloy is found down here in the metallic bonds. All right, so just showing you what the questions look like and how you're going to work them out. You'll have to do a few yourself. Lastly, problem 3. One of those two compounds, one of them actually can form a molecule in the vapor phase. And so you'll look up, you may be given these values here, but even if you look up here, the electronegativity difference, this one's larger. So that one's more of an ionic character than this one. So the tin chloride is less ionic, so more likely to be have more covalent character. So if this actually occurs, you'd have a guess that it's the tin chloride, not the lead chloride. And lastly, one of the other points in the syllabus somewhere, which is best applied here now that we've done all 3 types of bonding, is the melting point trends across the periodic table. And so here they are on a graph, and you'll find that these ones that have very low melting boiling points are the diatomics or the noble gases, because they're simple covalent molecules, or they're just gases that don't react with anything. The ones that are the highest are the ones that can form covalent network solids, and so those ones are got lots of covalent bonds, high melting boiling points. Within a similar range of the transition metals, because they have a large number of delocalized electrons and very positive nuclei, and so they form strong metallic bonds, whereas the S and the P metals have much larger ionic radii, and so their ability to attract the electrons is much weaker, and so their melting boiling points are less. And so that hopefully explains most of it. When it's in a compound, it's completely different. They will have to analyze that separately, as we did for the different videos.